Hello, welcome to SQL Bits. My name is Hugo Cornelis, and in this session I am going to talk about execution plans. It's a beginner level session. It's called Execution Plans. Where do I start? So, let's start. My name is Hugo Cornelis and I make SQLServerFast.com. SQLServerFast.com is my website where, as the biggest part of the website, I have the execution plan reference, providing a lot of documentation about everything you ever want to know about execution plans. It's a reference, so it's not beginner level. But I try to make it as complete as possible. It's a work in progress, though it's not completed yet. I also have something called the SQL Server Execution Plan video training. Short at this time, but it will eventually be very long series of videos that you can watch to learn everything I know about execution plans. I have other stuff on my website as too, such as my blog, some articles, and a section called resources where I have slide decks and demo code for all the sessions I present, including this one. I do a lot of other stuff too. You don't care about that. What you care about is how to find me if you have questions after this session, which is by email or on Twitter, and how to find the demo, the slide deck and the demo code I'm going to use now, or of my other sessions, which is also on the slide here. As you see, just go to SQLServerFast.com, click Other Presentations, Presentation Resources. You will see a list with all the sessions I have available. You can just download it and use as you wish. So for today, the agenda is that first I'm going to talk about why execution plans are relevant, then I'm going to show where to find them, and of course, most important, how to read them. After that, I will talk a bit about properties, the hidden part of execution plan that is so relevant and so often overlooked, and I'll finish by showing some examples. The first thing, why should I care? Well, you are here watching this session, so I guess you already have an idea of why execution plans are relevant. But I will talk about it anyway and maybe give you a better idea of why they are relevant. Or maybe it gives you some idea of how to convince others that they should start caring about execution plans too. So to understand the problem that the execution plan can solve, we first need to look at the difference between traditional third generation languages, also called procedural languages, such as C Sharp or C++ or Visual Basic or many others, versus SQL. Now when you think about third generation languages, that is basically a developer giving the computer exact instructions step by step of what to do. For people who never coded programs before, I like to compare it to my morning ritual, where I describe my morning ritual as switch off the alarm, go to get out of bed, go to the bathroom, brush my teeth, take a shower, get dressed, have breakfast, go to the office, start work. Because computers are best at doing the same task over and over very fast, those programming language, the third generation code often has to deal with large collections of data and just do the same thing over and over in something called a loop. And how those loops are built and how multiple loops interact, that's often where a developer can make choices. And the choice they make is called an algorithm. And here's the thing, if the developer picks the wrong algorithm, the code will run slow. And then someone will blame the developer for writing slow code, which makes sense because it's their fault. And then the developer can fix it, replace the algorithm, and deploy a faster version of the code. That's third generation. Let's move to SQL. And this is not specifically SQL Server. SQL is a language that all relational databases use, and they all have basically the same ID. So SQL is a language that doesn't describe step by step what the computer should do. SQL is a language that describes the end result. Give me a list of all people living in the Netherlands that we have in our database. I don't care how you make that list, give it to me. Or going back to my morning ritual comparison, my boss is like the fourth generation language of morning rituals. She will just call me and say, we have a customer in the office tomorrow, so make sure you're in the office by 9 and look representative. And she really doesn't care whether I set my alarm at 6 so I can have a very long breakfast, or whether I set my alarm at 8 and have my breakfast in the car. She doesn't care whether I brush my teeth before or after showering. She just cares that at 9 I am in the office looking sharp. And that's the same with SQL. I don't care how the computer gives me the results of my query. I just want them, and I want them fast. So the query describes the results we want logically in an all-at-once fashion. But in reality, computers cannot do everything at once. In reality, it's still step by step. So the computer has to make a translation from this all-at-once description in the query to a step-by-step implementation a processor can run. And this is done by a piece of software called the Query Optimizer. And every relational database has their own, and I'm going to talk about SQL Server's version, which is thousands of hours of engineering effort, thousands of hours of research, and as a result, it is incredibly good. Almost every query you throw at the Query Optimizer, it can come up with the best and fastest way to execute that query and give you your results by picking and choosing the correct algorithm. However, I said almost every case. It's still a fallible process. Sometimes, not often, but sometimes things go wrong. And then a query runs slow. And guess who gets the blame? Me. Yeah, my boss will call me and say, hey, your query is slow. And I can say, no, it's not my fault. It's the Query Optimizer. I didn't make it slow. You know what my boss will say? I don't care. Fix it. And she's right, of course. That's my job. But now I have a problem, because how do I fix something that I didn't mess up myself? So let's pin this down to SQL Server, where the SQL dialect used is called Transact SQL or TSQL. This is a language that allows a mix of those set-based queries with procedural code. So that means that sometimes when code is slow, it's simply because I used procedural code and picked my own algorithm and I picked wrong. On SQL Server, the best fix is just not to use procedural code. When possible, please use queries with set-based code. This is not true for all relational databases, but SQL Server is optimized to execute set-based code as fast as possible. So if you don't use that, you miss out. So what if I analyze the code and I find that there's just one single query, and that single query is slow. That single query is why the query doesn't finish in time. Now I have a problem, because I can look at the query and the query says, I want this result. And the optimizer says, oh, I am smart and I can come up with a very good algorithm to do this. And it runs slow. How do I fix that when I didn't pick the algorithm, when I don't know what algorithm is picked? Well, at least that last part is something I can fix, because I can know what algorithm is fixed. That is why execution plans are relevant, because by looking at the execution plan, I can see the choices the optimizer made. I can see the algorithm that the optimizer picked, which means that I can see why that specific query ran slow. What choice of the optimizer caused it? And that is the first step to then the second step. What can I do to give the optimizer better options, or to give the optimizer better information so that it picks the better option that was already available? So that's why we care about execution plans. Which obviously brings us to the next question: where do we find these execution plans? And that question can be answered in two different ways depending on your use case. So let's say you're a DBA on a production server and everything runs sluggish, or it's constantly spiking CPU, or it's trashing memory, and you don't know where the problem is. It's a busy server, hundreds of queries going on every time. you need to find which queries and which execution plans cause the problem. That's a very valid scenario. It's not in scope for this session. So here on the screen you will see several tools that you have available. I'm just calling them, that's all. And at the end of the session I will show a slide with resources. One of them is Grant Fritchie's book, and Grant Fritchie extensively discusses all of these options. So if that's a problem you have in your work and you haven't read Grant Fritchie's book yet, go download it now. Well, after the session. Not now, I'm talking to you. Be polite. So what is in scope for this session is if you have a specific query. So you are that DBA and you found the query that's causing the problem, or you are a developer and your DBA found the query and says you need to go fix it. So you are given a query, that query is slow, and you need to figure out why. So let's jump into a demo to see how we can approach that. And as you see, let's zoom a bit. So as you see, this query is, well, yeah, if a query calls a function called delay, I can figure out why it's slow. Obviously, that's not, let's switch to the right database. Obviously, that's not realistic. This is just a demo. In reality, the solution will not be in your eyes like this. For this, I can fix performance without looking at an execution plan. But let's assume it's not this simple. I can select a single query or multiple queries and click this button. It's called Display Estimated Execution Plan. I'll come back to that name later. And if I click that button, SQL Server will show me the execution plan. Bottom half of the screen shows the execution plan. I'm not going to talk about what it represents at this time. That will be later in this session. But this is one way to get an execution plan. It's not the only way. I can also use this button, which is called Include Actual Execution Plan. Another name I don't like, but it's the name it has. And if I click it, you will see that it just is indented and nothing more. I have now activated an option. And with that option active, when I execute the query, and this will take some time because the query is slow, of course. But once it's finished, you will see that an extra tab is opened in the results called Execution Plan. And if I click it, I see that same execution plan I saw before, but now with some additional data added that was not available at first. Additional data that was collected while the query was executing. In more recent versions of SQL Server, there's also a third option where you see a part of that data that is collected at runtime while the query is running. So if I disable this option and enable this option, called, I should hover first, called Include Live Query Statistics, and I've included that now, and run it, then you will see that the execution plan appears immediately, and then the query starts executing, and some of the runtime counters are updated while it executes. This version contains less runtime counters than the execution plan with all runtime statistics, but at least it shows them while it is executing the query. And if your query runs for 2 hours and you can already see the problem after 1 minute of watching this screen, you have just saved 1 hour and 59 minutes, because the execution plan with runtime statistics only appears when the query is finished. So those are 3 ways to find the execution plans. The first one I showed is the execution plan, or if you want to avoid a confusion, execution plan only. It is also called an estimated execution plan, and I really hate that term because the name suggests that the plan is just an estimate. And I see many people, I still find it on the internet every now and then, people saying, yeah, the estimated execution plan is what SQL Server thinks it will do, but when you actually execute the query, it might change its mind. That's not the case. When you ask for an execution plan using that button called Estimated Execution Plan, you tell SQL Server, here's a query, I want to execute it, go give me an execution plan. The optimizer starts building the execution plan. When it's done, it says, I have your execution plan, now you can start executing. And at that point you say, haha, fooled you. I'm not going to execute it at all. But you get the same execution plan that you would have gotten if you wanted to execute the query, because that's what you told SQL Server. You told SQL Server, figure out how to execute this, and then at the last second you said, I'm not going to do it. So the plan shown is how it will be executed. And yes, the slide says with some exceptions, those have to do with recompiles. Sometimes during a process, especially in a batch with multiple statements, there may be a reason why a plan is recompiled, and then you get a new execution plan, which might be different. But that's not because a difference between an execution plan only and an execution plan with runtime statistics, the next slide. It's because it's simply a new compilation. So the second version I showed is the execution plan plus runtime statistics, or execution plan plus for short, which used to be called the actual execution plan, which is equally confusing because it again suggests and reinforces the idea that estimated and actual execution plans are different things. Here's what I think I'm going to do, and here's what I actually did. But that's not how it works. Here's how I'm going to do it, and here's how I planned to do it with some statistics on how it actually went. That's what happens. Because if you run a query with execution plan plus enabled, it starts the same way as when you just request an execution plan. The optimizer is told to process a plan for the query. And then the query will execute using that plan, and during execution it adds some counters that are added into the plan. So you will get the same plan as the execution plan, only with the runtime statistics added. And then finally the execution plan with live statistics, only on newer versions of SQL Server, called live execution plan for short. Again, the optimizer just compiles the plan as it always does when you want to execute a query, and then the plan is immediately shown at that point without runtime statistics. And then while the query executes, Management Studio constantly polls for the runtime statistics and shows them during execution, constantly updating them. I already explained for long-running queries what benefit this can have. So here's a complete overview, and I'll just switch off my video for a few seconds so you can actually read it. I'm not going to explain everything that is on this slide. It's a lot of information. It's there just as an overview so that you can check it later. I'm not going to talk about all the details here. What I am going to talk about though is how to read execution plans. Because we now found them, we obviously want to use them. We want to understand what they tell us. So here is a very simple example execution plan. And if you look at this execution plan, you will see two different types of elements. The first one are the icons, small pictures, and every icon has a name below it, and every icon is a representation of a thing called an operator. I like to consider an operator as a small program that does some very specific task, a very specialized worker program. We'll talk more about those operators later, but first I'm going to show that the arrows are the second element within the execution plan. Those arrows represent data flows. And here's the surprising thing. If you look at the actual execution plan, which is XML, then you will find that those arrows are not there. The data flows are not even actual elements of the execution plan. I'll get back to that later as well. But first let's dive a bit deeper into those operators, the icons, the small programs that all have their own specific task. Now, if you go into the details of that, you will find that every operator has exactly three functions. And for a programmer, it will be, you could say that every operator can be called using three access methods or three entry points. One of them is the initialize call. And if an operator is called to initialize, it means that it's going to prepare to work. This will always be the first call to every operator when the execution plan starts running. But an operator can be initialized multiple times if during execution something figures out, oh, we need to restart this operator from the start. And during this restart, it is possible to change some of the parameters. So an operator that reads specific data from a table can first be asked to read the specific data for London and can then later be reinitialized and then can be said, we need to read all the specific data for Manchester. The most important call to an operator, the one that you will almost always focus on when trying to understand an execution plan, is the get next. What get next does is return a single row to the calling operator. So when an operator calls another operator, and that other operator is called with the get next, and it needs to return a row. That means that the operator has to produce that row, and in most cases, in order to produce that row, it has to ask other operators to return rows to it. And then finally we have the close operator, which is just called at the end to clear up anything, and it's really irrelevant for understanding how the execution plans work, other than, oh, great SQL Server, great that Microsoft remembered to clean up everything. That's all we need to know. The term operator is unfortunately an overloaded term. It is used in multiple ways, which can be confusing, and I am not going to fix that. I'm going to use the term the same way everyone does this, in the same confusing way. So let's try to explain that first. When talking about an operator, we may be talking about a generic type of operator. We might talk about the filter operator as a filter operator does specific things. On the screen you will see, I think this is a copy paste from the execution plan reference, which explains why it's not easy to read. Simplified, it would say the filter operator reads rows, applies a test, and then passes the row if the test is true. And that is the same for every operator of this class of operators. However, the term operator is also used for an instance of an operator within that class. So a coworker might come to me, point at an execution plan and say, hey, I see 3 filter operators in this plan, and that one makes sense to me, but that one, I don't understand why it's there. And then he's not talking about the class of filter operators, but about one specific element within that class, one specific operator within that class. And both are using the term operator, which can be confusing, but most of the time the context makes clear what we mean. Now the arrows, I already mentioned, they are not even actual elements of the plan. They don't exist in the SQL. And yet we see them in the execution plan on our screen. So the arrows represent which operators can call other operators. The reason why that is not persistent in the XML is because that is implied by how the elements are ordered in the XML. So the arrows are a visualization of the ordering in the XML, which represent which operators can call which other operators. Because, as I said before, most operators, when they need to return a row, do so by first asking rows from other operators, by calling them. So when you look at the structure, it is important to realize that every operator in an execution plan will always be called by and return rows to exactly one operator, which makes the calling operator the parent operator and the called operator the child operator. The reverse is not true. Many operators call one other operator too, but there are also operators that don't call other operators. And there are operators that call multiple other operators. This results in something that mathematicians call a tree in graph theory. And because of this link to graph theory, operators within a plan are sometimes also called nodes, which is also a term from graph theory. Now the reason I call those arrows data flows is, like I said, the arrows represent which operator, whoops, misclick there, sorry. The arrows represent which operators can call which other operators, but every call is responded by returning a row. So if operator A can call operator B, then operator B returns rows to operator A. So data flows from B to A, and that's why the arrows are often seen as data flows. The arrow direction is actually the data flow direction and not the call direction. So when reading execution plans, there are some very common and very annoying misunderstandings. And one is the cost percentages. SQL Server loves to show cost percentages and people love to misinterpret them. So here we have another demo. And again, this is a very simplified and completely unrealistic example. But let's assume that this query is slow and that after significant work I tuned it to this version. Now, if I run these queries, if I select both queries and just ask the execution plan only, and I'll move this slider up a bit, and then zoom in, you will see that the first query has a cost of 99% and the second has a cost of 1%. Now you can't see it in zoomed in, but when I zoomed out, you will see that these numbers are described as the query cost relative to the batch. So I have a batch of two statements, the old statement and the optimized statement, and the optimized statement is just 1% of the total cost. I'm a query tuning god, right? I am awesome. And then people will come at me and say, yeah, but you asked for an estimated execution plan, and maybe the actual execution plan is different. Well, I'll humor them. I know that they are not different because it's the same execution plan, but let's try anyway. So I'm going to execute these queries and look at the actual execution plans, as those people call them, at the execution plan plus runtime statistics. And what do we see? Still 99%, 1%. I made the query 100 times faster. I am awesome. Except, yeah, those percentages are dangerous. So let's switch off the execution plan. Let's switch on to other options, statistics IO and statistics time, to get some other insight in what's actually happening. And now when I run the same batch, I will see in the messages that the first query, the slow one, took 60 milliseconds CPU time, 12 milliseconds elapsed time, and did 689 logical reads. And I made it faster, right? Because now it took, 67 elapsed time, and it did almost 100,000 logical reads. That's not faster. Oops. So what's going wrong here? Let's look at the execution plan one more time, and I'll show why these 99% and 1% are so misleading. The 99% is based on this number, the estimated subtree cost, which is 0.584 for the first query, and for the second query, it's 0.006, which is indeed a much lower number. But it's the estimated subtree cost. Now this is in an execution plan with runtime statistics, but it's still the estimated cost. SQL Server guesses that this is how much the query will cost when creating the execution plan, which is before the query runs. And it doesn't update that during execution running. There is no runtime statistic for the actual cost. So the only cost that Management Studio has available is the estimated cost. And based on the estimates, the second query will run faster, but the estimates were wrong in this case. And now that you know that this estimate is wrong, do you still trust this estimate? This estimate? I hope not, because this estimate on filter, 3%, is based on the estimated operator cost relative to that number we saw before as the estimated subtree cost of the entire query. Again, based on estimates. So it is very dangerous to look at those percentages because we don't know how good those estimates are. So yeah, it's deceptively easy to look at those percentages and immediately zoom in on the high percentages. But often it's just deceptive. It's based on the estimated cost, whether you use an execution plan only or an execution plan plus runtime statistics. The percentages you see are based on estimated costs. So if your estimated row counts are wrong, those percentages are wrong. And here's the kicker. If your estimated row count is correct, the estimated cost can still be wrong, because those estimates are also based on generalized hardware assumptions. They are not based on your specific hardware. The same percentage would come on every computer for the same query with the same input data, regardless of your hardware. So one query may have faster memory and slower CPU. Another computer may have completely different settings. They will have the same costs. So even when your row count estimates are correct, the percentages you see as the cost percentages can still be misleading. This is the part where I normally try to be interactive with the audience, but yeah, remote doesn't work that way. So I'll just answer the question myself. Many people will tell you when I ask this, oh, an execution plan should always be read right to left. And they will tell you that because a lot of websites on the internet and even a lot of books will tell you that. It's not true though. You should also not read them left to right. You should read them in whatever order makes sense, and you should understand what each order means. So let's look at what happens when an execution plan such as this actually runs. What happens is that the select operator, which isn't a real operator, the select operator represents the client that asks for rows, calls the get next of the filter. And as I said before, many operators, when called, need to have data first. So filter will ask the table scan for a row by calling its get next. Table scan will then read data from the table and return it to the filter operator. And the task of the filter operator is to do a check. Is this row relevant for this query or should I discard it? Well, this is a row we need to discard. So filter asks for another row. Table scan returns another row. Filter repeats the test, and if this row is good, then it is returned to the select operator, which of course immediately calls for the next row. The blue arrows represent the data flow. Table scan returns data to filter, and filter represents to select. The red arrows represent the order of control. Select calls filter, filter calls table scan. Both orders are relevant. Because of how execution plans work and how data works, complex execution plans are often, but not always, best understood by starting at the right side and following the data. But not always. There may be operators that have some setting that cause an entire branch not to be executed at all. Well, start at the end, figure out the entire branch, spend 2 hours, and then find an operator that says, oh, I'm not going to call this branch. That makes you feel rather silly for just wasting 2 hours, right? So you don't always want to start at the end. You sometimes need to start in the middle. You sometimes start top left. It's just what the execution plan calls for. And sometimes I just start in the middle with a section that looks suspicious. Where you start is not really relevant. How you read them is not relevant, but you need to understand the flow of control order, left to right, and the data flow order, right to left. Now we have talked about how to read execution plans. Of course, you still need to understand what all the operators do, but that's beyond the scope of this session. I do want to point out something called properties, and that's because what we look at when you look at an execution plan is just the tip of the iceberg. So the graphical execution plan you see is just the part of the iceberg above the water. And as with any proper iceberg, most of it is hidden below the surface, in the properties. Let's look at a demo to understand why execution plan properties are so important. So here we have two very different queries, and I'll switch to the correct database. I have two very different queries. And when I look at the execution plans, they appear the same. Now when two execution plans appear the same, the execution plan tells the execution engine how to work. So how is it possible when I execute these two queries that one returns almost 20,000 rows with a lot of columns, and the second query returns less columns and also less rows, even though the execution plans are identical? How is that possible? The answer is below the surface. We're now looking at the tip of the iceberg. Let's look below, and for instance, by hovering the clustered index scan, I see this pop-up that shows some of the properties, and it shows, for instance, a long output list. It's not even complete. The dashes, the dots here show it doesn't show everything. When I look at the second execution plan, the output list is much shorter and has only the 5 column names returned. So this is how the execution engine knew to only return those 5 columns. And we see a predicate here that tells the execution engine we don't want all rows, we only want the rows for which this condition is true. Now I already pointed out that the property list of this operator is incomplete, and that is shown here as incomplete. I would like to know everything. Well, I right click and I say properties, and in my case it only activates a window I already had active, the properties window here. I personally always leave that window open. So when you leave that window open, you don't have to right click. I can just click anywhere in any execution plan, and if you look at the properties window to the right, you will see that whenever I click somewhere, the data changes because it shows the properties of that operator. And if I go to the clustered index scan that has this much too long output list, I can go here, click on the button, and then I will see all the data in there. Or I can just click here on the ellipsis. That's the wrong place. And then I will see a separate window where everything is. So all the data is available in the properties window, and some of it is available in the pop-up. So I already showed this, I included it on the slide for completeness. If you hover over an icon, you will get a subset of the properties for that operator. What you see is not configurable. Microsoft determined that. I don't always agree with their choices. You can also, I did not show that in the demo, but you can also hover over an arrow. And if you do that, you get a even smaller subset of properties. Not for the arrow, because the arrow doesn't exist in the execution plan, but for the operator to the right of that arrow. And the properties you see are focused on how much data is produced by that operator. You can see that in the screenshot on the slide. Then there is the properties window, and I did show that. You can right click an icon and select properties, or you can just leave the properties window open. I showed it in the demo. Now, I already mentioned in passing that the top left operator is not a real operator, but still it has properties. Those properties are properties for the plan as a whole, and I'm going to briefly show some of them in the next demo. So if I go to the select operator and activate, you will see that the pop-up window is very short, but in the properties window, and I'll just pull it out for a second now so that I can enlarge it a bit, you will see a lot of properties. And some of them are very relevant. Let's look at a few. So, for instance, here I can see that this query ran as a serial plan. Here I can see which version of the cardinality estimator was used. SQL Server has different versions of this. It's out of context for this session, but if you already know what it means, then here you can see which version is used. You can see, if I expand this plus, you can see information about something called a memory grant. Here you can find information about the hardware that the optimizer knows it has available. Here you see information about how long the query took to run, which is extremely valuable, and when I jump out of the zoom it, I will show this in more detail. You will also see information, for instance, about trace flags, about wait stats, and there is even more that is not visible in this demo because it only shows what is there. If you have a parameterized query, it will show information about the parameter values that were used at compile time and at runtime. As promised, the query time stats, if I expand that, you will see how much time, how much CPU time was taken and how much elapsed time was taken while executing this query, which is very useful because if you forgot to enable set statistics IO, then you can find the same information here. So I just touched upon the properties of the plan as a whole. There's a lot of information there. It's very valuable, and you should always look at the properties on that top left operator. For other operators, you will find that if you look at the properties, it's data about that specific operator. And some of them determine how the operator behaves. They can influence how it behaves. Some of them give runtime information. Some of them give yet other information. It's extremely useful, and you really need to look into that to understand execution plans and to understand what happened. What all the properties mean, what they are, is absolutely not in scope for this session, but obviously because execution plan reference is a reference, I try to describe everything there. Luckily, most property names are just English and are fairly self-explanatory. Not all, but most are fairly easy to understand if you just look at what the name says. So to finish this, I'm going to run through one example of the two I have available. And in the interest of time, I will not run the second one, but you can play with that yourself. And I will show what you can learn from looking at an execution plan. So let's jump into the correct database. So if I execute this and look at the execution plan, you will see that this execution plan is already more complex than what we saw before. And you will see several things happening. And let's start at the top right with an index seek. An index seek is an operator that uses an index to quickly find data. And what data it finds can be found in the seek predicates. So here you will find that it finds data for product ID equals 710 in the sales order detail data. And here you will see the output list what columns it returns. That's the sales order ID and the sales order detail ID. Now this is interesting because if I look at the query, I will see that I did in fact search for product ID 710, but I don't care about sales order detail ID. I never asked for it. So why do I get this? This data then flows to a nested loops, which means that for every row from the index seek, it will call its bottom input and it will initialize it again. So this key lookup will initialize and execute multiple times. And every time it executes, it will return some data based on sales order detail ID and sales order ID. So this is why the index seek returns sales order ID and sales order detail ID, so that the key lookup could be used to find the order quantity, data that was not available in the index used here. So the result of this nested loops plus the index seek and the key lookup is that we now have data from the sales order detail table for product ID 710 found by looking in an index and then using the pointers in that index, the clustered index columns, to find the rest of the data. This might already be a tuning opportunity, because what if there was an index available that has the order quantity as an included column? Every indexing choice you make has benefits and downsides, so perhaps it shouldn't be done. Perhaps this query is better left as is. But perhaps if this query is important enough, then this is a way you can optimize it, and you can find that from the execution plan. Another nested loops then goes into a clustered index seek on the sales order header, where it basically just does what is in the join condition. It finds the sales order header with the same sales order ID. But you also see that the order of the joins has effectively been reversed. SQL Server decided I can better start with the sales order detail, filter it on product ID, and then join to the sales order header. After that, data is sorted and then led into a stream aggregate. Aggregation is what you do get for a group by. It can be done in multiple ways. Stream aggregate needs sorted data. And here the optimizer apparently decided that sorting it and then using a stream aggregate is the cheapest option. So you can look at the sort. And if you want to know exactly what it does, you will see that it orders by customer ID. That's because the stream aggregate needs to group by customer ID and it needs the data to be sorted. And here you will see that it does indeed group by customer ID, and it outputs the customer ID and then two new columns called expression 1002 and expression 1003. What are those expressions? Well, that is unfortunately not in the pop-up, so now I need to click it to enable the full properties window, and I can go to something called the defined values. You will find that here. You can expand it, or you can just use the ellipsis to get it in its separate window, and then you will see that expression 1002 is in fact a count star, and expression 1003 is defined as a sum of the order quantity column. And you will see I highlight the relevant stuff because how SQL Server works and how optimization execution plans work, There's a lot of brackets and parentheses in those expressions, and learning to read them is an acquired taste. And then finally we get a top-n sort, which is a combination of a sort and a top-n. That's because we need to order by total quantity and then get the top 10. SQL Server combines that into a single operator where it sorts by expression 1003, which is of course the sum, descending, and it selects, and you cannot see that here, but you can see it here. If I do it correctly, you can here see that it selects the top 10 rows only. And this is an optimized sort to quickly find the first 10 rows. Now if I look at the second query, and I'm not going to explain this because I'm running out of time, but here you will see a completely different execution plan where completely different choices are made. The reason these different choices are made is because it's effectively the same query, but now for product ID 711. And SQL Server expects, based on its estimates, much more matching rows. And when there are so many more matching rows, then other choices become cheaper. And that's the part of the optimizer that says, for product ID 711, I really need to use a different algorithm. So I don't have time to walk you through what those choices are. I'm going to wrap up now. I do recommend, if you are interested, to read SQL Server Execution Plan's 3rd edition. Do not read the earlier editions. It was hugely updated and improved when Grant rewrote it for the 3rd edition. It's an excellent guide from getting started to the intermediate level. You can download it for free from the Redgate website. I have created a tiny URL so that you can quickly find it. If you want a paper copy, you can order one from Amazon.com. That's not free. But if you want a PDF, you can download it for free, no strings attached. I mentioned already the SQL Server Execution Plan reference and the Execution Plan video training. And then on pluralsight.com there's lots of good courses. Of course, you do need a Pluralsight subscription to view them. That's all I have. If you have questions, please mail me, please tweet me. I'm happy to talk with you. Again, go to sqlserverfast.com to download the slide deck and the demo code. Thank you for watching. Enjoy the rest of SQL Bits. Bye bye.